In this lecture, we will discuss electric generators of wind turbines. I will briefly show you the position of the electric generator as a component in the wind energy transition, the basic principles of electrical generator, and finally, we will discuss opportunities and challenges generators are facing in the future. Here, you see the position of the electrical generator as a component in the whole wind energy transition system. As we can see, the generator functions as a secondary energy conversion device. It takes mechanical energy from the blades and converts it to electrical energy. The electrical energy will be processed later on by power converters to certain voltage levels and frequency before it is collected by cables and transformers. The electrical generator is an electromechanical energy conversion device. It has a rotating component called rotor and a stationary component called stator. It has both mechanical and electrical ports. Between the rotor and the stator, there is the air gap. The electrical generator has both mechanical and electrical ports. The energy conversion process from the mechanical port to the electrical port relies on the interaction between the magnetic field in the air gap and the current in the stator. The torque the generator can deliver is therefore proportional to the product of the magnetic flux density in the air gap B, the current loading per unit length along the air gap circumference A, and the volume of the rotor VR. As we also know, the power of the generator P is calculated from the product of the torque T and the rotating speed omega. Now we can draw a conclusion. The volume of the generator rotor is proportional to the power and inversely proportional to the rotating speed. If the power and the speed are fixed, the product of current loading A and the magnetic field density B determines the size of the generator. The higher the product, the smaller the volume. Therefore, to reduce the size of the generator for specific power output, we should either increase the product of B and A or increase the rotating speed of omega. However, none of these can be arbitrarily chosen. In real electrical machines, magnetic field density is determined by magnetic saturation level of the material. Current loading A is limited by ohmic loss in the conductors. The rotating speed is on one hand decided by the tip speed of the blades, and on the other hand, limited by the gear ratios from the blade shaft to the generator shaft. Therefore, the larger the wind turbines, the slower the blades. A higher gear ratio means higher number of gear stages, which lead to higher failure rates and maintenance cost, which is very critical for large wind turbines. Let's now have a look at the trend of the development of the wind turbine generators. As we can see from the figure on the left, the wind turbine size is growing bigger and bigger in past years. There are several motivations for going larger. First, with a higher tower, the blades can get higher wind speeds to generate more power. Second, with the increase in size, the material cost emission and loss per unit energy is reduced. The other trend is the wind energy industry is moving from onshore to offshore. The motivation is quite straightforward. There is much higher wind speed and nearly unlimited space offshore. The development trend of wind turbine brings challenges and opportunities to the wind turbine electrical generator in the future. Let's first look at the growing size of wind turbines. As the size grows, the rotor speed decreases because the blade's tip speed is limited by noise emission. Recalling from the sizing of the generator, with a lower rotational speed and even higher power, the size of the generator will grow exponentially. The increased size of generator means higher losses and also brings problems to mechanical supporting. Now let's look at the other trend of the going offshore. Comparing to onshore, the environment offshore is more aggressive. Humidity, condensation, and corrosion may make electrical generators and power electronics fail more often. On the other hand, the cost of logistics, maintenance, and installation is far higher than onshore. The generator system offshore should have higher reliability. These challenges also bring many appealing opportunities to further development of electrical generators in the future. Let's look at two examples. To solve the sizing problem, we may adapt superconducting materials in future generators. Superconducting materials allow current flow and generate a magnetic field without ohmic losses. Thus, the magnetic field density and current density can be increased to reduce the size of the generator. Another possibility is to make the generator system modular. By designing and manufacturing the electrical generator in a modular way, the generator can be transported as individual modules and installed on-site. It will cut the logistics cost for offshore wind. Moreover, in case one of the modules fails, the failed module can be bypassed. In this way, the system availability can be increased. The maintenance period can be extended, which are crucial for offshore wind. As a conclusion, the wind electrical generator is limited by many factors. Because of those limiting factors and development trends, there will be many challenges and opportunities in electrical generators to bring more wind energy in the future.